DNP3 Basics, Lesson 6, Application Layer, Application Header. Everything you learned so far has one purpose: to send application data between a master and outstation. The first 5 lessons covered the other parts of DNP3 protocol. The last 7 lessons cover the application layer. Application data consists of an application header and a set of objects. The application header contains general information about the application message, including a function code describing why the message is being sent, and, for messages from an outstation only, a set of internal indication flags that contain outstation status information. This lesson covers the application header, including internal indications. The application header appears right after the transport octet and are the initial octets of the application layer. The header in master messages is 2 octets in length and contains the application control and function code octets. The header in outstation messages is 4 octets in length. It contains the same 2 octets as in the master header and is followed by 2 internal indication octets. The application control octet, the first octet of the application header, looks something like the transport header. Fur is set in the first application fragment of a possible series of more than one. Fragments contain up to 2048 octets. Multiple fragments can occur when there are many events or for outstations with a large amount of static data. Fin is set in the final application fragment in a series. Like the transport layer, fur and fin are both set when one fragment contains all requested data. The astute observer may notice that the most significant bit in the application header is the fur bit. The most significant bit in the transport header is the fin bit. Why the difference? No one is sure, but we suspect this part of the design was done over a few beers. The con bit is a request for this message to be confirmed once it has been received and processed. Confirmation is required in a few cases. The most common is an outstation message reporting event data. To ensure events are not lost, events are retained in the outstation memory until confirmed by the master. The con bit can only be set in messages from an outstation and is not allowed to be set in messages sent from a master. Continuing on with other bits in the control octet, UNS indicates that this is an unsolicited message. Unsolicited messages are discussed later, but basically there are 2 types of messages sent from an outstation. Solicited messages are sent in response to requests from the master. Unsolicited messages are set spontaneously by the outstation to report events, and only if the outstation is allowed to send unsolicited messages. SEQ is a 4-bit sequence number, 0 to 15. For solicited messages, each message sent from the master uses a sequence number 1 more than the prior message. Each outstation response uses the sequence number in the master request. When a request causes a multi-fragment response, each fragment after the first uses an increasing sequence number. Numbers wrap from 15 back to 0. Sequence numbers sent in unsolicited messages use a different sequence than solicited messages. The sequence number in each unsolicited message is one more than the prior unsolicited message, again wrapping after 15 back to 0. But the unsolicited message sequence is unrelated to the sequence numbers used in solicited message responses. For a little more information about sequence numbers, the sequence number is used by the outstation as a way to make sure the master received the response to a prior request. In normal operation, each request should have a sequence number incremented by 1 from the prior message. If a request is received by an outstation with a sequence number the same as the prior request, and if the rest of the message is also the same, then the outstation assumes the master lost the prior response, so it resends that response. If any part of the message differs, sequence number, function code, etc., then the outstation processes the request as a new message. You may notice using this logic that the sequence number could have been designed as a single bit. The outstation processes all messages with a new sequence number, the same as any new message. It does not matter if the sequence number has incremented by some value other than 1. The second application header octet is the application function code. DNP3 defines many. Some are rather obscure and are not part of the subset definitions, which means they will not be discussed in this class. We will only talk about subset admissible function codes and their subset admissible uses. So please be aware that there are more function codes and possible uses than presented here, but it is also okay if you do not really care. The uses of most application codes will be more obvious in future lessons, but I will present one example now. It is the most common one. The master sends a message with a read application function code that specifies a set of data to read. Function code 1 is read. The outstation responds with the requested data in a message with a response function code. The response function code value is 129.
Note the same application sequence number in the request and response.
And now a little bit more about the CON bit. The application header CON bit is what the outstation uses to request confirmation that a message is received by the master. The most common use is sending events. An outstation is responsible for making sure events it sends are actually received and processed by the master. It does this by setting the CON bit in the application header for any message with events. The outstation retains events until it receives confirmation that the event message was received. As soon as the master receives and processes a message with the CON bit set, it sends an application message with the confirm application function code. On reception, the outstation can finally get rid of the sent events. Reception of any message other than a confirm message causes the outstation to make sure events are not discarded and to resend them in the next applicable message. A successful confirmation exchange looks like this. The master issues a request to read events. The outstation responds with the events requested, in this case one event, and sets the con bit. The master receives and processes the message and sends a message to the outstation with the confirmation application layer function code. Outstation application messages include an additional 2-octet field called internal indications. Each of the 16 bits in this 2-octet field indicate something about the outstation. Some meanings may not make sense now, but will before the last class. Bits in the first octet are the broadcast bit in the least significant position, which means that the outstation has detected a broadcast message, one sent to DNP addresses 65, 533, 4, or 5, which are hex FFFD, E, or F. The next bit, C1, says there's at least one class 1 event not yet sent to the master, followed by C2 for a class 2 event and C3 for a class 3 event. We will talk about those more later. The next bit is the need time bit, is set when the outstation needs to have its clock synchronized. Then the LOC bit, which means that at least one output point at the outstation is in local mode, meaning a control action sent to that point will not be processed. The next bit is the trouble bit, meaning something is wrong at the outstation. Anybody's guess what it is. DNP3 does not define anything other than there's problems. And the most significant bit means the outstation has restarted. So the master should reset this bit by writing a 0 to it and then proceed with steps needed to reinitialize the outstation. The second internal indication octets starts with 3 error IINs in the low 3 bit positions. These each indicate that there is some error in the most recent message sent from the master. In reality, it matters little which flag is set, as they all mean the prior message had a problem that was not processed. But the bits are: the function bit says there was no support for the application function requested in the prior message. The object bit says the object requested was unknown. Objects are defined later. And the PE bit says there's a parameter error. That's any error that does not fall under the function or object IINs. The other IINs in this octet are event buffer overflow, meaning at least one event was lost because the outstation ran out of space to store it. The already executing flag that's sent in response to a command request, such as a relay or analog output, indicating the command could not be processed because another operation was in process that blocked the new request. And the next bit is configuration corrupt. Again, there is no definition of what this means, but the outstation likely cannot continue if it responds with this bit set. The upper 2 bits of the second octet are unassigned but are reserved for future use by DNP. So that's the end of this lesson. What did we learn? 1. Application messages from a master start with a 2-octet header. Application messages from an outstation start with a 4-octet header. that contain the same first 2 octets as the master header, plus 2 octets of internal indication information. The application header fin and fur bits can accommodate large messages that require more than one application fragment, 2048 octets. A response with the conbit set requires confirmation by the master. The most common use case is when the outstation reports events. Regarding internal indications set by the outstation, if any of the low 3 bits in the second internal indication octet are set, there was an error in the previous request. Some of the other internal indications provide information about the outstation that can be acted upon by the protocol, such as need time, and still others report serious issues that may require physical corrective action, such as device trouble. And there are a lot of application function codes and internal indication flags that we have not discussed. So it might be a good idea to keep notes on information in the tables presented above for use in later lessons.